Hello, how are you? How are you doing? It's me, the pioneer, is the Tunisian researcher Mourad Sultan Ezouidi. Today we will see, uh, we'll apply Ezouidi theorem, and we will see how the Ezouidi theorem works, and we will see also how can we solve a 9-degree polynomial equation using or applying Mourad's Sultan Ezouidi theorem. So first of all, as usual, I am Professor Mourad Sultan Zwidi, and today you are about to witness a breakthrough in mathematics. For centuries, mathematicians believed that finding exact solutions to polynomial equations of degree 5 or higher was impossible. Abel's theorem told us the door was closed. But what if I told you that today we are opening the door, or we are opening that door, the door that Abel's theorem closed, okay? That we are going to construct, not to approximate the exact roots of 9-degree polynomial equation using pure algebra, symmetry, and Ezouidi theorem. This is not theory only, it's verifiable and it's symbolic and it's published. Today, you will see exact roots built from radical and roots of unity, fully satisfying an equation, and and you will see that classical method failed to solve. Let's begin, my kids. The third example I told you I will do it. Okay, let's start. So this is, I will share this one.
Degree polynomial equation, so x to the power of 9.
This
Right,
one,
and how
x
a
to the
particular
power
method is
9.
used to find its roots. It looks like a real beast on paper.
It does. It's a dense forest of numbers and notation when you first look at it. Think x minus 18 by o plus, well, a whole lot of other terms following that.
Exactly. It's the kind of thing that could easily make your eyes glaze over.
Mhm.
So our mission here
Easy
is
to
really
solve
to,
it. Okay,
navigate
without
through
using
that
Mourad
density
Cut
Sultan,
through the
we will never
calculations
solve
shown
this
in the
kind of
source.
and pull out the key
problem.
insights
Okay.
because apparently there's a surprising result when this specific method gets applied to this specific polynomial.
Yeah. And the real question is, can something that looks this complicated, this mathematical beast, actually be tamed? Can it be simplified if you find the right way in?
Let's unpack it. Let's see what the source shows us. Okay, so where do we begin? The source starts with the polynomial itself, sets the stage.
Yep. This specific ninth degree equation, highest power of x is 9.
The source gives the whole thing. Px equals xr minus 18xo plus 144 by xr minus 672 by arrows. It just keeps going.
Plus 2016 Niagara minus 4032xr plus 53376xr minus 436 plus 2304x minus 513 equals 0. Phew.
That's a lot of terms, a lot of coefficients.
Yeah.
And the source labels these, right? Using lo.
Well, yeah, all the way up to there. So L's is 18, low is 144, and so on. These numbers basically define this specific complicated polynomial.
It's DNA, like you said, makes it look pretty unwieldy.
Okay, so that's our starting point, this big complex thing.
So how does the source suggest we, well, tackle it, find the roots? This is where the method comes in, I guess.
Yes, exactly. The source talks about a formula, or maybe a discriminant formula, from someone named Mourad Sultan Ezouidi HM.
Mourad Sultan Ezouidi H's. Okay. And the point of using this formula is what exactly?
Well, according to the source, the goal is to find the exact roots of the polynomial.
The exact roots.
Yeah.
Not approximations.
Right. And the method works by calculating a whole new set of coefficients. They're labeled is coefficients in the source.
Ah, okay. So you go from the L's to the S's.
Precisely. They're derived systematically from those original coefficients. The source shows these, well, fairly complex looking general formulas for calculating each is value based on the L's.
We probably don't need to get lost in the exact notation of those formulas here.
No, not at all. The key thing is there's a defined process. You plug in the L values, you do the calculation shown, and you get these as values out.
Okay, so the source takes this polynomial, identifies its as coefficients.
Yep, the 18, the 144, etc.
And then feeds them into this Mourad Sultan Ezouidi Hism formula to generate these news values.
Right. And this is where, as you suspected, things get interesting. Quite surprising, actually.
Okay, I'm ready. What happens when they calculate these as values for this polynomial?
So the source goes through the steps, calculating S zeros, S, and so on.
Yeah.
And it states that S is 0.
Okay.
Then SES is calculated, also 0. S is 0, S is 0. SAO, Euro, DES, they all come out as 0.
Wait, hang on. S all the way through S's are just 0.
Every single one of them, according to the calculations shown in the source.
That seems incredibly significant. What about say?
Well, SES isn't 0.
Mm.
The source shows the calculation gives S equals 99.
Okay, so after all that crunching with this specific method on this specific polynomial, almost all the resulting S coefficients just disappear. They become 0, except the very last one, SES, which is 99.
Exactly. It's a massive simplification hiding in the process.
So how does that simplification play out? I mean, how do these S values relate back to the original polynomial Px?
Well, the source shows that the original polynomial Px can also be expressed using these as S coefficients. The general form is given as Px x plus SES plus as S, and so on down to minus 0.
Ah, I see where this is going now. If SSSS up to Usho are all 0.
Right. Then the term SS set becomes 0 times x, which is 0. The term plus x becomes 0 times x, also 0.
All those terms just vanish.
Every single one from the x term down to the x term. Their coefficients are 0, so they're gone.
So that huge expression, Px xx plus x, all the way down to a 0, 0, it just boils down to what?
It collapses dramatically. You're left with just Px equals 0, 0.
Wow. And we found SES is 99.
So the equation becomes x minus 99 equals 0.
Or simply XX equals 99.
Bingo! That's the aha moment the source leads us to. You start with this incredibly complicated looking 9th degree polynomial defined by 9 different non-zero OPEC coefficients.
Yeah, the one that looked like a nightmare?
You apply the specific analytical method from Mourad, Sultan, Ezouidi, Gesem, and it transforms the problem into simply finding the 9th roots of the number 99.
That's quite a trick.
It really is a striking transformation. Suddenly, instead of grappling with all those terms, we have a much, much simpler problem to solve.
So the source then shows how to solve XX and 99.
It does. And finding the 9th roots of a number like 99, well, that involves complex numbers. You don't just get one answer.
Right, there should be 9 distinct roots in the complex plane.
Exactly. The source uses the standard way to find these. It gives the formula for the roots. Let's call them xk. It involves the principal 9th root of 99.
Okay, like the positive real number that when multiplied by itself 9 times gives 99.
Sort of, yeah. It's written as 99, the 9th root of 99. And then you multiply that by e raised to the power of 2 times k times I times pi, all divided by 9.
The classic roots of unity part.
Precisely. And k here goes from 0, 1, 2, all the way up to 8. That gives you the 9 distinct complex numbers, xk, that solve xxe into 99.
Got it. But those xk values are the roots of the simplified equation. How does the source connect them back to the roots of the original complicated polynomial?
There's one final step shown, a transformation. If the roots of x99 are xk, then the roots of the original polynomial, the source calls them ak, are found using a formula. Ak plus xk9.
Okay, and L. That was the coefficient of x here in the original polynomial, but with a minus sign, right? So x at x was 18.
Correct. XL equals 18, so you plug that in, xk plus xk9.
And xk is that complex expression we just talked about?
Yeah.
The 9th root of 99 times 8.
Yes, so you substitute that in, ek, 18, plus 18, 9. But then the source shows something quite neat.
Another simplification.
Kind of. It seems that due to the specific way this method works and the structure it imposes, that 99 factor, in the context of this particular transformation formula relating xk and ak for this problem,
Welcome to the deep
effectively
dive.
simplified.
This is where we take the source material you
presents
shared with
the
us.
and today it's some pretty interesting excerpts from a PDF all about polynomial root finding.
Right, and our job is to help you cut through the, let's say, the density of it all and get straight to the core insights.
Exactly. We want to pull out what really matters for you.
So what are we diving into specifically today?
Okay, so today we're looking at a really specific, quite advanced mathematical problem that's in your document. It's a 9th degree polynomial equation.
A big one.
Yeah, and not just the equation, but a very particular method laid out for finding its exact roots. The text attributes this method to Mourad, Sultan, Ezouidi, Hism.
Ah, okay. So likely not the method you'd find in a standard first-year algebra textbook.
Definitely not. It seems quite specialized, laid out step by step in your source just for this kind of thing.
So our mission for this deep dive,
is to unpack that specific process, the one shown in your source. We want to follow the steps, try to understand the logic, see where it leads. What results does it actually give for this equation?
Makes sense. Let's get into it. Where do we start?
Let's start with the polynomial itself, the main event.
Okay.
Your source gives this specific ninth degree equation. It's px equals x arrow minus 18 by arrow plus 144 by arrow. It keeps going.
A lot of terms. We probably don't need every single one right out, but it goes all the way down to x and then a constant term at the end. It's, substantial.
It is a bit of a monster, like you said.
Yeah.
The source then does something standard. It writes it in a general form using these coefficients, L euro through lec.
Right. So px equals x minus L euro xx plus lec is minus LQ x air, and so on. The signs alternate.
Exactly. And crucially, your document gives the specific numbers for these L coefficients for the polynomial we're focused on.
Yeah, I see them here. LEO is 18, Leonardo is 144, LERO is 672, then lec is 1, which is interesting. And then Ilshu is actually negative, minus Sun 6 is 118, and some other big negative ones later on too, like for LOQ and OQ. And LQ is 1 again. Finally, LQ is 2538256X.
So that's our beast, defined by those specific OL values. Now, how does the source suggest we tackle it? This is where the unique method comes in.
Okay. It explicitly says it uses the formula of Mourad, Sultan, Ezouidi, Hism, and also something called the discriminative formula of Mourad, Sultan, Al-Community, H's.
Right.
And the core idea, it seems, involves calculating a new set of coefficients. The source calls them SK1Q or sometimes SK1R. These S values are somehow derived from the original OL values.
Okay, so we transform the L's into S's, and your source actually shows the results of these calculations. And this is where it gets, pretty interesting.
How so?
Well, after all the calculations, which look quite involved, the summary section in your document shows that for this specific polynomial, many of these new SES coefficients, they just turn out to be 0.
Really? Which ones?
Let's see. SCI, AOI, SECA air, S air, SA8C, all 0.
Wow, okay. That can't be random. That feels like a key property this method has uncovered about this particular polynomial.
Exactly my thought. So if most of these S values are 0, what does that let the method do?
Well, this seems to be the clever part of the approach presented in your source. Because so many S coefficients are 0, the source then takes that original huge 9-term polynomial and simplifies it dramatically. It basically says, let's look at a related polynomial that only uses the terms corresponding to the S coefficients that weren't 0.
Ah, okay. So it focuses on something like px equals xx, and then which S terms were left.
Looks like CES and CES were the non-zero ones, or at least the ones used next.
Precisely. The simplified equation shown is pxxx plus xx plus xox equals a 0. All the other terms corresponding to the zeros values are essentially dropped for this step.
Okay, interesting. And does the source give values for CES and S euro used here? You mentioned CES wasn't in that list of zeros. It does. And you're right, such wasn't listed as 0 in the summary, but it's used here with the value 13,220,415. And SR, which the summary implied was non-zero, is used with a huge value, 683,999,482,673.
Got it. So the big complex equation gets boiled down to this much simpler 3-term version, xs plus sxx equals 0, 0, using those specific calculated numbers for ses and sesh.
Yes. And now the task is to solve this simplified equation,
which looks much more manageable. How does the source proceed?
Well, the first obvious step, looking at xio plus xl plus xx equals 0.
Right. So you get x times x plus x equals plus x is.
Exactly. And that immediately gives you one root for this simplified equation.
X up.
Yeah, one down. One down. Now we need to solve the bit inside the parentheses. X plus s and x plus x plus s as arrow.
Xs plus xs plus arrow is there. That form looks familiar. It's only got powers of x's in it, essentially.
Precisely. If you make a little substitution, say let a will xs.
Then xu is I squared. Aha. It becomes I plus s equals 0. That's just a quadratic equation in y.
Exactly. It has the structure of a quadratic.
Oh.
And that's how the source seems to approach it. It uses something related to the quadratic formula to solve for xio, which is our y.
Okay, so how does it apply that? Does it calculate a discriminant for this quadratic in xio?
It calculates a related value, yeah. It calls it psycho. And it's calculated as minus AO squared plus 4 times xio.
And does it give a value for that?
It does. For this equation, sec comes out as a very large negative number, minus 172,482,673. 43,374,841,533.
Wow. Okay, negative. So using that SAT and the value for SAT, the source then plugs these into the quadratic formula structure to find out.
All right. The formula looks like XCO equals minus plus or minus.
Here, my colleagues, we start with a 9-degree polynomial equation, and we apply the theorem of Mourad and Ezouidi, and we calculated, let's say, the new coefficient of the new 9-degree polynomial equation that corresponds to the original 9-degree polynomial equation, and we find that S0 is 0, S1 is 0, S2 is 0, S3 is negative 13,220,415, and S4 is equal to 0, S5 equal to 0, and S6 is equal to 0, S7 is different to 0, S8 equals 0. You see here S8 equals 0 means immediately the first root is clear. It's L042 divided by 9. Okay? Means here, if you are going to go back to your equation, what is the first coefficient? Is 18. 18 divided by 9 is 2. So the C is the first real root. Simply because why we divide 18 by 9? Because S8 is equal to 0. The last coefficient of this new 9-degree polynomial equation is equal to 0 means the first root is 18 divided by 9, which is equal to 2. Okay. Then we'll obtain a new 8th-degree polynomial equation, x8 plus s3 x4 plus s7. This is a quadratic equation. Just set x or y equal to x4, we will obtain a 2nd-degree equation in terms of y. Okay, then you use the discriminant of me, which is s1 of 42 dash equal negative s3 squared plus 4 times s7. This one is equal to a negative number. Okay, but look, the new polynomial to the power, the new 2nd-degree equation that corresponds to this. Okay, it will be s0 for the q is 0 always, x squared plus s1 for the q equals 0. I'm looking for x squared. I should transfer s1 for the q on the right hand side. So it comes minus s1 for the q. When you write s squared equal negative s1 for the q dash, means you will take the square root of both sides. So it comes here negative sign. That's why here S1 is negative. Now minus S1 is positive. Because positive S1 will be transferred on the right hand side. It transports with that negative sign. Okay? We continue.
It's the square root of minus CIO all divided by 2. It's minus CIO under the square root because CIO itself was negative, so minus CIO is positive.
Ah, okay, that makes sense. So we're taking the square root of a positive number. Does it show the results?
Yes. Plugging in the numbers for SIRS and the square root of negative 0, which the source approximates, it calculates 2 specific positive real values for XOL.
What are they?
One is approximately 51,942.20 SIR.
Okay.
And the other one is much larger, approximately 13,168,472.80.
Right. So, recap. For the simplified equation, we found x of CO is a root, and now we found that XO must be equal to one of these 2 positive numbers.
Correct. So the final step to get the roots x for the simplified equation is to find the 4th roots of these 2 numbers.
Okay. And for any positive number, there isn't just one 4th root, right?
No, there are 4. For any positive number, A, you have the positive real 4th root, the negative real 4th root, and a pair of complex conjugate roots.
Your source actually mentions how to find these.
Yeah, it gives the general form. This is the roots of the principal 4th root of A, let's call it OA, multiplied by e to the power of k times pi times I divided by 2, where k can be 0, 1, 2, or 3. That covers all 4 roots.
Got it. So we take the first XA value, that 51,000 number, and apply this formula for K0, 1, 2, 3. That gives 4 roots X. Then we take the second XA value, the 13,000,001, and do the same thing. Apply the formula for a K0, 1, 2, 3. That gives another 4 roots X.
Correct. So that's 8 roots in total from the 2 XAO values.
Plus that XAO root we found earlier.
That makes 9 roots, which is what we'd expect for a 9th-degree polynomial, even the simplified one.
Okay, so that seems to solve the simplified equation. But what about the original monster polynomial we started with? How do these 9 roots relate back?
That's the crucial connection. The source addresses this right at the end. It talks about the roots of the original polynomial, calling them alpha.
Okay.
And it presents a formula. It suggests that these alpha roots are related to the roots we just found, let's call them xk, by a transformation. The formula shown is XA L arrow plus X day 9.
Wait, L arrow, that's the coefficient of X here from the very beginning, right? The
Yeah.
18.
Exactly. So the proposed relationship is 8 plus X day. It suggests you take each root xk from the simplified equation, divided by 9, add 18, and that gives you a root ac of the original equation.
Huh. That's a
Yes.
very specific transformation.
It is. And there's one more interesting thing the source states right after this formula. It says something like x as 2. The notation is a bit unusual, but it strongly points towards the number 2 being significant.
2. How does that fit in? Let's try that formula. What if we take the simplest root we found for the simplified equation, xk equals 0?
Okay, plug xk0 into x18 plus xk9.
You get x18 plus 0, 9, which is 18, 9. That's 2.
Exactly. So the transformation formula, when applied to the xe root of the simplified equation, yields exactly 2. And the source specifically calls out 2. It seems this method has highlighted 2 as potentially a key root or value related to the original polynomial.
Wow. Okay. That ties things together quite neatly. So let's try and summarize this journey for you, the listener.
We started with your source material presenting this really complex 9th degree polynomial,
Defined by those specific OL coefficients. Then the source introduced unique method attributed to Mourad, Sultan, Ezouidi, Ezouidi.
The core of this method involved calculating a new set of coefficients, the S coefficients.
And the critical finding for this specific polynomial anyway was that many of those coefficients were 0.
Right. And that allowed this method to transform the original complicated equation into a much, much simpler 3-term equation involving only x, a dose and x.
Solving that simpler equation was more straightforward. Factoring out x gave the root x eurus immediately.
And the remaining part, x plus a x ostra plus yogo equals 0, could be treated like a quadratic equation in XO.
Solving that quadratic gave 2 positive values for XO.
Then finding the 4 fourth roots, real and complex, of each of those XO values gave another 8 roots for the simplified equation.
So combined with x0, that's the full set of 9 roots for the simplified form.
And finally, the source provided that intriguing transformation formula, ik plus ak9. This suggests how the roots xk of the simple equation might relate to the roots ek of the original complex one.
And crucially, applying this formula to the xa's root directly pointed to the value 2, which the source explicitly highlighted.
So what this deep dive really uncovered is not some universal standard technique, maybe, but a very specific, detailed pathway presented in your source for analyzing this particular type of high-degree polynomial.
Yeah, it relies heavily on those coefficients turning out the way they did. It shows there are diverse, maybe less common mathematical tools out there.
Absolutely. We went from this dense equation, followed this unique method based on Ayres coefficients, saw it simplify the problem dramatically, found roots for the simpler version, and then saw this transformation linking back and highlighting the number 2. It's quite a specific mathematical narrative.
What really stands out for me is that simplification step, how calculating those Addo's values just collapsed the complexity. And that final formula, egg, Euler plus xk9, connecting everything back via that first coefficient, it's quite elegant in a way.
It is. It really makes you wonder, doesn't it? How do these very specialized methods, like the one shown here, compare to more general numerical or classical approaches for finding roots? Are they faster, more accurate, or only applicable in very specific cases?
Yeah. And are there other kinds of transformations, other sets of derived coefficients maybe that could unlock the structure of different complex equations in similar ways? What else is hiding in there?
Good questions to think about. Definitely food for thought.
Well, thanks for sharing this fascinating mathematical exploration from your source material and joining us for this deep dive.
My pleasure.
Thank you and goodbye, my colleague. This is an example how we master the solution of a 9-degree equation and how my theorem values all the coefficient and solve the problem with any mistakes. Okay, means here we don't approximate, we give exactness using this theorem, and this theorem has been generalized for any n-degree equation. Okay, prepare yourself to be familiar with this new theorem. Thank you and goodbye.